Hi, Natasha. Thanks so much for joining me on this episode of Concentrating on
Thanks
Chromatography. I
for having me.
appreciate it. Today, the plan is to focus on the educational side of separation science. And certainly, I spend a lot of time speaking with academics about their research. We don't focus so much on the role of the instructor and some of the challenges. So I appreciate you coming on. Can you tell us about your current role as an instructor?
I'm a junior professor, so I just graduated. I just started teaching. So I'm currently teaching general chemistry, and I did an organic chemistry lab as well, and also introduction to chemistry. Separation science, I think I've been teaching like the foundations of separation science, concepts like polarity and melting point, boiling point, solubility. Those are all introduced in general chemistry and analytical chemistry, and then in organic chemistry as well. And that's kind of mostly what organic chemistry lab is. It's isolating and purifying and characterizing different molecules. And they do things like extraction and distillation, TLC plates, mini column chromatography with like a little pasture pipette. It's really cute. And then they characterize with things like iris spectroscopy, NMR, or finding the melting point.
And I know the answer might be all of the above, but what types of students are you working with?
All of the above. So the university that I work at, La Sierra University, it's kind of a feeder school into Loma Linda University, where we're kind of sister schools with them. And I literally like got my PhD from Loma Linda University, and I came back to teach it last year. Like we're very close schools. And Loma Linda University is a healthcare institution, and so most of my students are actually pre-professional. So they're pre-medicine, pre-dentistry, pre-pharmacy, pre-PA, physician's assistant, or pathology assistant, pre-physical therapy, pre-vet. I can go on, pre-nursing. But yeah, so my students are pretty much mostly going into healthcare. There's like maybe one or two every once in a while who go into actual science and it's all science, but who go into like a PhD or grad school to actually do a research project. Most of them are going into a professional school of some sort. But yeah, so we actually don't have a lot of chemistry majors. We have mostly biochemistry majors. Biochemistry and chemistry, though, are like obviously sister subjects, and it all comes out of the chemistry department, which is where I work. And so, yeah, the majors are very similar, but biochemistry, I think, is where most of our students land because they are pre-professional and want to work in healthcare.
And at what point in their education do students typically encounter separation science? And
It's tricky because I don't know if it's ever really labeled as separation science. Like, there's no class on separation science. There's not like a chapter called separation science in the textbook, right? So they might not even realize that that's what they're learning or understand the importance of it. But like I said before, general chemistry starts going through those concepts of separation science, like all of the different ways to characterize and background information of how separation science works, like with polarity and solubility and stuff. And so they learn the background of it, but I don't think, I remember I taught this last quarter, um, like the background of polarity and solubility and stuff. And I don't think I ever said, and this relates to separation science, like that's not really a thing. But so I don't think they realize that that's what they're learning. But general chemistry starts going through those concepts. They really put into practice in organic chemistry lab and analytical chemistry as well.
and there might not be a specific answer to this question, but where do you think traditional chemistry education might fall short in discussing these concepts in general?
I think we should talk to students more about actually classifying it as separation science so they know that's what they're actually being trained in. I think a lot of times students are learning the key concepts, but they don't realize it. And I think a lot of students, especially because last year is such a feeder school into Loma Linda University, I don't think they realize there's other jobs in science that they could do if they have a science minded brain and they want to go into some field of science. And so I think it'd be really cool if we had specifically a separation science class or applications of separation science or something more applicable. I mean, we do have an instrumental analysis class where you learn all the different instruments and stuff, but I think the chemistry education falls short in that it's hard to put all of the knowledge that they accumulate into practice unless they do actually research with us and stuff.
And are there some of the first concepts in separation science that students tend to struggle with?
Yeah, what I've seen so far, it's when they have to start analyzing infrared spectra or from iris spectroscopy or NMR, nuclear magnetic resonance spectra. When they start having to analyze that in organic chemistry, I start seeing them get confused. And I think that's when they start struggling a little bit because it requires a little bit more critical thinking versus like when they do the TLC plates or when they do the column chromatography, it really is just, you really don't have to understand the science behind it. You really could just be like, okay, like they do a lab in organic chemistry where they separate out the pigments of spinach. And you really could just follow the steps and not really have to think. You just have to follow what's on the paper. And so there are plenty of students who are great students who I don't think they understand the significance of what they're doing. It's just, let's just do it, get it done, get out of lab as soon as possible. I think they first struggle, really struggle with when they have to read the IR spectra and NMR spectra and understand it and like write a lab report on it and stuff because that is the first time they have to critically think about their results and not just follow the instructions and spit out a result.
And are students getting enough exposure to real world sample preparation challenges?
So I think in class and lab alone, they do get a lot of experience in prepping samples and doing those kind of concentration, dilution, titration calculations. But again, I don't think they realize the significance. Like, I don't think I've tried to tell them, but I don't think they realize, like, oh yeah, these dilution calculations, I did those every day in grad school. Oh, these like concentrations, these buffer calculations, I did those every day as well. Like, I don't think they realize that the experience they're getting is like intentional because these are real skills. So I don't think they grasp that it's like really building their foundation in prepping samples and real world sample prep and stuff. So I would say the real experience comes from when they do research on the side. So a lot of students do research on campus in the biology or the chemistry departments. And that's where they learn how to do like more of an applicable sample prep on a much bigger level and also learn how sample prep factors into like real applied research versus in the lab when like again they might just be following the protocol or acting as like doing whatever the sheet tells them to do.
I'm going to rephrase this next question, but how well do you think the curriculum is keeping up with how fast analytical techniques are evolving?
I think the goal is that curriculum is always constantly evolving to keep up with analytical techniques, especially in upper division classes where there's a little bit more flexibility, right? And you get people who are more interested in like the actual chemistry of it all and like doing research projects and everything like that. So like the older students or the upper division students and stuff. Um, However, like, I mean, budget cuts and everything, right? We don't know, we can't keep getting the most recent technology, the most recent instrument, or the most recent everything, as it's coming out because, every education, every every department is struggling right now financially. And so I think we keep up as much as we can. And the goal is always to try to keep up, at least if even if we can't have like the specific piece of instrumentation or the specific materials to do the new and evolved methods. I think we try to at least share literature and at least try to understand where the new techniques are going, if that makes sense.
I think you bring up a great point of the cost of the
Hmm.
instrumentation. My sense would be a lot of curricula struggle to keep up with the modern pace of how things
Hmm.
are changing. But it's one thing that there's change. It's another if you simply can't acquire that technology, and how do you instruct on the latest and greatest if you don't actually have it in front of you? It's much different than when I was in school where there wasn't a whole lot devoted to digital marketing. It was more like these are the core
Mhm.
concepts, but technology was moving so fast that it was really hard to keep that textbook up to date, let's say. But there wasn't a major hurdle in terms of an acquisition that would prevent you from teaching it. So it's kind of those two things
Mhm.
at the same time.
Yeah. No, I totally understand that.
Do students come in thinking that separation science is something simple and easy to understand, or is it more intimidating?
So I don't think they think about it at all. And I'm sorry if that offends you as a man who's committed to their life of your career to separation science. But I don't think, again, because we don't intentionally say like, oh yeah, this is your first entryway into separation science, or like, oh yeah, this is like the first time you're doing X, Y, and Z. Or I guess when we do TLC plates and when we do chromatography and stuff, we do call it chromatography and call it TLC. But I don't think they think about it in terms of like, oh, this one concept is intimidating or simple. I think they think about it in terms of like the whole class. Cause again, I teach like the lower level classes, general chemistry, introduction chemistry, organic chemistry, and stuff. And so I think students go into those classes more intimidated about the class itself and about like the content of the class and getting the good grade so they can go on to their professional program and stuff. I don't think they're thinking, oh yeah, this one lab that we're doing like the TLC plate or doing the IR or the NMR is intimidating. But I'm not sure. I'll have to talk to more of them and ask them about it.
And for something like mass spec, how different is the classroom versus how it's actually used in the lab?
It depends on what level we're talking. We don't actually use that much mass spec. We do spectroscopy at a low level in general chemistry, but we don't use mass spec on a huge level in the lower levels of chemistry. I will say, I think even when it is used in the higher levels of chemistry, the way it's used in a classroom is very different to the way it's used in the lab. In the lab, you have researchers doing tens, 20s, hundreds of samples, right? And taking the spectra, analyzing the spectra, and that's their job, right? In the classroom, they get one sample, maybe three, maybe they do three trials if the lab is ambitious, right? Three trials of something and then take the samples and that's it, right? And take the spectra and that's it. And so I think in the lab, it's a very broad view of mass spectroscopy and other types of spectroscopy and other types of separation science because they're really doing like one experiment or one version of it. Unless again they do research and then maybe they'll do like 10 samples or 20 or 30, but it's never on like a as big of a scale as it is used actually in the lab by like researchers and the professionals in industry and stuff.
And are there specific places where students struggle with that transition between theory and then actually using the instrumentation in a hands-on way?
I don't think there is a transition between theory and hands-on instrumentation. So like between because it's taught separately and also kind of together. Like for IR spectroscopy or NMR spectroscopy, which is like what I've seen in organic chemistry, right? They'll learn the concept in class and then they'll come to lab. And like in class for their classwork and stuff, they're also analyzing spectra and also trying to understand spectra. So it's not like there's a big transition. In class, they're still learning the theories behind it. And they're still learning how to do it. I guess like um the only transition I can think of really is sometimes again like when students are working on an experiment or whatever from lab, um sometimes they're just acting according to the instructions in the lab manual. They're not really thinking about the theories behind what they're doing. So, like, I remember in organic chemistry, like the first lab, they do like some SN1, SN2 reactions, and they don't comprehend that that's the reaction that's actually happening. Even though they write it down in their lab notebooks, they don't comprehend that that's the actual reaction that's happening. They just do the protocol as written, you know?
No, I think that's a good indication that the classroom or textbook educational portion is working and that students are prepared for when they get that hands-on work and that
Oh,
it goes smoothly. It's not like they read about it and then when it's in front of them, none of what they learned applies. So I think that's
mhm.
probably a good sign. Are there concepts that are maybe overemphasized in education, but are less critical in real
Yeah,
workflows?
I think it depends, right? So in education, you learn kind of broad scopes of most concepts, right? And then in real workflows, you usually only use like it depends on what your research project is. And so I think everything that you learn in your education and in your classes and stuff can be important depending on what you do with it, depending on what your workflow is, depending on what field of science you're going into, depending on what kind of experiments you'll be doing.
And is there anything that you wish students understood before they ever touched an
Yeah,
analytical system?
I wish they understood more of why they're doing what they're doing. Because again, students sometimes just follow instructions and they're great students and they try their best and stuff, but they're just following the instructions and doing exactly what like the lab manual tells them, but they don't actually understand what they're doing. And, like, I can see signs of that when, like, in simple things, like, if the instructions say, like, "Yeah, get an ice bath about half a liter," I'll see students measuring exactly point 0.5 like, exactly half of a liter, where, like, an ice bath, it doesn't matter. It can be a little bit above or below the halfway line, and so if I see students being, like, overly specific in certain things, I'm like, "Oh, you really don't understand what's going on, like, in this experiment because like or in this workflow because you if you did, you would know, like, that would be an approximation or that would be less important to focus on or whatever. So when it comes to instrumentation, before they even touch a system, I wish they just fully understood the concept of the concepts behind it, what's actually going on in the instrument, which I think instrumental analysis classes are really good for. And we have an instrumental analysis class where they learn like actually what happens inside each of the instruments. So before they touch a system, I just hope they understand why they're doing what they're doing, the results that they're going to be getting, and why it's helpful and how it's helpful, and yeah, and how to best treat the instrument. Is to treat the instrument kindly and stuff.
So, from your perspective, what skills separate a good chemistry student from a great one?
So besides the obvious answer of just the same thing that separates any great student from a regular student, no matter the subject, is just caring about about the class and about and putting in the time and effort, right? But that's for any student, not specifically chemistry. I think chemistry, because again, I teach the general chemistry and then it gets more and more specific as you get higher up, right? You have general chemistry, then you have organic and analytical and biochemistry and physical chemistry and a bunch of different specific branches of chemistry, right? And I think at the general chemistry level, you have to make peace with not with certain concepts being more broad and like know that like yeah, there's a smaller, more specific there are more specific understandings of this topic, but we're just not going to get to it in this class. And if you want to get to it, take another higher level class. And so I think skills that separate a good chemistry student from a great one um, is yeah, putting in time and extra care and everything, but also knowing when it's okay to not fully know all the tiny little details and just move forward and understand the big picture and when to zoom in. So just being able to make that distinction, um, I think is what makes a good chemistry student, a great chemistry student, I mean.
Do you have any concerns that students are being trained more on button pushing rather than understanding what's actually happening under the hood, as
Yeah,
they say?
and I think a lot of students, they're so concerned with doing everything perfectly and correctly that they don't fully understand what's going on, right? And they don't understand the purpose of what they're doing and like the significance of what they're doing, or even just taking a second to be excited about what they're doing. They're just so focused on trying to get it right and trying to get it correct and trying to get their A, you know? Because again, I mean, which is understandable because they have so much pressure on them to get into their professional programs. Because again, I teach a lot of pre-med, pre-dent, pre-farm, a bunch of pre-professional students. And so they're so concerned with their grades because they have to be, and I understand that. Um, but sometimes that detracts from them actually understanding and appreciating the science and what they're learning. And so, yeah, definitely, I'm concerned all the time that students are more learning to be button pushers and more learning to just follow a set protocol and um, follow a set lab manual rather than learning how to critically think and learning how to understand things and appreciate the science and um, the bigger picture, I guess, because they're just so focused on getting that A and getting a great grade. And it's good. It's a good thing, I guess, overall that they're trying to get a good grade, but it's not a great thing to me that they're more focused on getting a great grade than on really understanding and appreciating the science. And I don't think they realize that, like, in trying to understand the bigger picture and understand and appreciating it, it will make them care about it more and it will help them get an A anyways, you know? So like I think they think it's separate. And I think a lot of students think like I don't have time to care or like try I don't have time to like understand and appreciate the science. I just have to get it and get what I need to get my A, you know? And I don't think they understand that they go hand in hand. And
And in some ways, you're in a much tougher spot, I suppose, than someone who just has a room of organic chemistry majors who they're instructing, where it's more likely that they'll be really excited about this type of work. Natasha, this has been great. I think this has been super insightful and learning more about how these core concepts are introduced. And yeah, I really appreciate the time,
yeah,
Natasha. Thanks so
thank
much.
you.